Hello everyone, and welcome to today's presentation. I'm excited to have you here. Today, we'll be exploring alcohols, phenols, and ethers, unveiling organic chemistry. We'll take a look at the fundamental concepts behind these important classes of organic compounds, their properties, and their significance in chemistry. So, let's dive in and uncover the fascinating world of these molecules together. Welcome to this next part of our presentation. Today, we'll explore the Williamson ether synthesis, which is a fundamental method for crafting ethers. Ethers, as you know, are compounds with the structure ROR or ROR, where the oxygen acts as a bridge connecting two carbon groups. It's a key reaction in organic chemistry because it helps us form these important molecules efficiently. Next, we'll look at the physical and chemical properties of alcohols. Understanding these properties is crucial because alcohols serve as the starting point for many other compounds, including phenols and ethers. For example, alcohols are generally polar, have high boiling points, and can form hydrogen bonds, which significantly influence their behavior. Moving on, we'll classify alcohols into primary, secondary, and tertiary categories. This classification is based on the number of carbon groups attached to the carbon bearing the hydroxyl group. It's important because it affects their reactivity and the types of reactions they undergo. We'll also touch on the applications of alcohols, phenols, and ethers in everyday life and industry. From solvents and disinfectants to pharmaceuticals, these compounds are everywhere and play vital roles. For those preparing for CBSE exams, key concepts like acidity and hydrogen bonding are essential. Alcohols and phenols differ in acidity, and hydrogen bonding influences their physical properties. Finally, we'll review some key reactions, such as Kalb's and Reamer-Timon, which are specific to phenols. These reactions help us understand how phenols behave chemically and how they can be modified for various uses. And last but not least, we'll clarify the structure and significance of the hydroxyl group in alcohols and phenols. The hydroxyl group, ROH in alcohols and RO in phenols, is responsible for many of their characteristic properties, including their ability to form hydrogen bonds and their reactivity. Throughout this presentation, keep these core ideas in mind. They form the foundation for understanding the chemistry of alcohols, phenols, and ethers. Today, we're going to explore the fundamental concepts of alcohols, phenols, and ethers, which are essential topics in organic chemistry. We'll look into their definitions, how they are classified, and their key properties. Additionally, we'll examine important reactions involving these compounds. Understanding these concepts is crucial because they not only deepen our theoretical knowledge, but also have significant practical applications in various industries. As we move through this presentation, keep in mind how these structures and reactions form the building blocks for more complex organic molecules. This foundation will help you appreciate the importance of these compounds in both academic and real-world contexts. Today, I want to talk about alcohols, which are a specific type of organic compound. They are characterized by having a hydroxyl group, which is a OH attached to a saturated carbon atom. This functional group plays a crucial role in determining their chemical and physical properties. Understanding this hydroxyl group is key because it influences how alcohols react and behave in different situations. When we look at alcohols, we're essentially seeing molecules where this group is bonded to a carbon chain, and that connection really defines their characteristics. So, as we move forward, keep in mind how significant this functional group is in shaping the behavior of alcohols within the broader context of organic chemistry. Now, let's talk about the different types of alcohols based on their hydroxyl groups. First, we have polyhydric alcohols, which possess two or more O groups. An example of this is glycol, or ethane 12-diol. You might recognize glycol as an antifreeze because of its ability to lower the freezing point of water. Another example is glycerol, or propane 1,2,3-triol, which is commonly found in cosmetics and food products due to its moisturizing properties. These polyhydric alcohols are important because their multiple hydroxyl groups give them unique chemical and physical properties. On the other hand, we have monohydric alcohols, which contain just one O group. Ethanol, with its chemical formula CH3CH2OH, is a prime example. Ethanol is widely known because it's the type of alcohol we find in alcoholic beverages, but it's also used as a solvent in many industrial applications. Understanding these differences helps us see how the number of hydroxyl groups influences their uses and properties. This classification is fundamental as we explore their roles in various chemical reactions and applications throughout this presentation. Let's take a closer look at how we classify alcohols based on the carbon atom bonded to the O group. When the carbon attached to the hydroxyl group is connected to 3 other carbon atoms, we call it a tertiary, or 3 degrees, alcohol. A good example of this is 2-methylpropan-2-ol. Next, if the carbon bonded to the OH is attached to 2 other carbon atoms, we refer to it as a secondary, or 2 degrees, alcohol. Propan-2-ol is a common example here. And finally, when the carbon with the O group is only attached to 1 other carbon atom, we call it a primary, or 1 degrees, alcohol. Ethanol is a typical example of this type. This classification is important because it helps us understand the reactivity and properties of different alcohols, which ties back to our overall theme of exploring their chemical behavior. Now, let's take a closer look at the physical and chemical properties of alcohols. These properties are fundamental because they influence how alcohols behave in different chemical reactions and applications. Starting with physical properties, alcohols typically have higher boiling points compared to hydrocarbons of similar molecular weight. This is mainly due to the presence of the hydroxyl group, which allows alcohol molecules to form hydrogen bonds with each other. As a result, alcohols tend to be more soluble in water, especially those with shorter carbon chains, because the hydroxyl group can form hydrogen bonds with water molecules. Moving to chemical properties, alcohols are quite versatile. They can undergo a variety of reactions such as oxidation, dehydration, and substitution. For instance, primary alcohols can be oxidized to aldehydes and then to carboxylic acids, which is a key pathway in organic synthesis. Understanding these properties helps us see why alcohols are so widely used, from solvents and fuels to key intermediates in chemical manufacturing. Their physical and chemical characteristics directly influence how they are handled, stored, and transformed in different industrial processes. Let's take a closer look at some physical properties of alcohols. First, you'll notice that alcohols have significantly higher boiling points compared to alkanes of similar molecular weight. This is mainly because of the strong intermolecular hydrogen bonding that occurs between alcohol molecules, which requires more energy to break apart. So, hydrogen bonding really influences their boiling points quite a bit. Moving on to acidity, alcohols are actually weak acids. Interestingly, primary alcohols tend to be more acidic than secondary or tertiary ones. This difference comes down to inductive effects, basically, how electron density is distributed in the molecule, which affects how easily the alcohol can donate a proton. Finally, regarding solubility, lower molecular weight alcohols are quite soluble in water. This is due to their ability to form hydrogen bonds with water molecules, which helps them dissolve more easily. Overall, these physical properties, boiling points, acidity, and solubility, are key to understanding how alcohols behave in different environments and how they compare to other hydrocarbons. Now let's talk about oxidation of alcohols. Primary alcohols, as you might remember, can be oxidized first to aldehydes and then further to carboxylic acids. This progression shows how the oxidation process can go all the way to more oxidized forms. Secondary alcohols, on the other hand, are oxidized to ketones, which are quite stable and don't go much further. Tertiary alcohols are resistant to oxidation entirely because they lack the hydrogen atom on the carbon with the hydroxyl group, making it impossible to undergo this kind of oxidation. Moving on to dehydration, under acidic conditions, alcohols can lose a water molecule. This is a key step in forming alkenes. Basically, when you heat an alcohol in the presence of an acid, it will undergo dehydration to produce an alkene, which is an unsaturated hydrocarbon. These oxidation and dehydration reactions are fundamental in organic chemistry because they allow us to transform alcohols into a variety of other useful compounds, tying into the broader theme of how we manipulate molecular structures in synthesis. Let's take a closer look at phenols, which are quite distinct from alcohols. In phenols, the hydroxyl group, or O, is directly attached to an aromatic ring, usually a benzene ring. This is a key difference because, in alcohols, the OH is attached to a saturated carbon atom. This direct attachment to the aromatic ring significantly influences their chemical properties and reactivity. Understanding this structural difference helps us grasp why phenols behave differently in various chemical reactions and how their properties are impacted by this unique bonding. Recognizing these distinctions is essential as we explore their applications and roles in different chemical contexts. Phenols are significantly more acidic than alcohols. This is mainly due to the resonance stabilization of the phenoxide ion, which forms after deprotonation. When phenol loses a hydrogen ion, the resulting negative charge can be delocalized over the aromatic ring, stabilizing the ion. This resonance effect makes phenols much more prone to losing their proton compared to regular alcohols. Now, just like alcohols, phenols can be classified based on the number of hydroxyl groups attached. They can be monohydric, meaning they have just one O group, or polyhydric, which means they have multiple O groups on the aromatic ring. This classification helps us understand their chemical behavior and acidity levels better. So, in summary, understanding the acidity and classification of phenols is crucial because it connects to their reactivity and how they can be used or modified in various chemical processes. Now, let's move on to the key reactions of phenols, specifically Kolb's and Reaumur-Timon reactions. These are important because they help us understand how phenols can be transformed into various derivatives. Starting with Kolb's reaction, this involves the decarboxylation of carboxylic acids in the presence of phenols, leading to the formation of hydrocarbons. It's a useful method to synthesize hydrocarbons from aromatic acids. Next, the Reaumur-Timon reaction is quite fascinating because it allows us to introduce a formal group, or CHO, onto the ortho position of phenols. This reaction uses chloroform and a strong base, typically sodium hydroxide, to generate dichlorocarbene, which then reacts with the phenol to give us salicylaldehyde derivatives. Both reactions highlight the versatility of phenols in organic synthesis. Kolb's reaction emphasizes the ability of phenols to participate in decarboxylation processes, while Reaumur-Timon showcases their capacity to undergo electrophilic substitution at specific positions on the aromatic ring. Connecting this back to the overall theme, understanding these reactions is crucial because they open pathways for modifying phenols into more complex compounds, which are often useful in pharmaceuticals, dyes, and other chemical industries. Now, let's look at how phenol reacts with chloroform in the presence of a base, such as sodium hydroxide. This reaction is quite useful because it allows us to introduce an aldehyde group specifically at the ortho position of the phenol ring, resulting in salicylaldehyde, also known as O-hydroxybenzaldehyde. This method is valuable in organic synthesis because it provides a straightforward way to functionalize phenol compounds selectively. Moving on, the Reaumur-Timon reaction is another fascinating transformation. In this process, phenol reacts with carbon dioxide in the presence of sodium hydroxide, followed by an acidic workup. The key outcome is the formation of salicylic acid, or O-hydroxybenzoic acid. Importantly, salicylic acid is a crucial precursor for manufacturing aspirin, making this reaction highly significant in medicinal chemistry and pharmaceutical production. Lastly, I want to briefly mention Kolb's reaction, which is another important transformation involving phenols, although it's a bit different from the previous ones. Together, these reactions illustrate the versatility of phenol as a starting material and how we can selectively modify it to produce a variety of valuable compounds used in everyday medicines and chemical industries. Ethers are a fascinating class of organic compounds, and what sets them apart is the presence of an oxygen atom that's connected to two alkyl or aryl groups. Think of the oxygen as a bridge, linking two carbon-containing groups. Now, these groups can be the same, which we call symmetrical ethers, or they can be different, known as unsymmetrical ethers. In the case of symmetrical ethers, the structure is ROR, where both sides are identical alkyl groups. For unsymmetrical ethers, it's ROR, with R and R being different groups. This oxygen bridge is a key feature that influences the properties and reactivity of ethers. Understanding this structure helps us appreciate their role and behavior in various chemical reactions and applications. Now let's take a closer look at the two main types of ethers. First, we have mixed ethers, like methoxybenzene, which has different groups attached to the oxygen. In this case, a phenyl group and a methyl group are connected via the oxygen atom. Mixed ethers are quite common and are often used as solvents because of their unique properties. Next, we have simple ethers, where both groups attached to the oxygen are the same. For example, diethyl ether, where two ethyl groups are bonded to the oxygen. This symmetry influences some of their physical properties. A key point to remember about ethers, especially when comparing them to alcohols, is that they generally have lower boiling points. This is because they lack the hydrogen bonding that alcohol molecules can form with each other. As a result, ethers tend to be more volatile and are quite useful as solvents in many chemical processes. So, understanding these two types, mixed and simple, helps us grasp their structural differences and how those differences impact their physical and chemical behavior, which ties back to their role in various applications throughout the presentation. Today, we're looking at how this process produces an ether, which has the general structure ROR. The Williamson synthesis is actually a very versatile method because it allows us to prepare both symmetrical ethers, where R and R are the same, and unsymmetrical ethers, where R and R differ. The key step involves the alkoxide, which is formed first, reacting with a primary alkyl halide. Represented as Rx, this happens through an SN2 reaction, where the alkoxide acts as a nucleophile and attacks the alkyl halide, displacing the halide ion. Before we get to that point, we generate the alkoxide by treating an alcohol with a strong base, like sodium metal. This step is crucial because it converts the alcohol into an alkoxide ion, RONA, making the oxygen atom a much better nucleophile for the next step. So, in summary, the Williamson ether synthesis is a powerful and flexible method for crafting ethers, and understanding each step, from alkoxide formation to nucleophilic substitution, is key to mastering this classic reaction. Mastering IUPAC naming conventions is absolutely essential for all three classes of compounds we've discussed. It's important to correctly identify the functional groups, determine the parent chains or rings, and assign the correct numbering to ensure proper placement of substituents. This consistency in naming helps us communicate clearly and avoid confusion in chemical identification. Moving on to intermolecular hydrogen bonding, this is a critical concept because it explains why alcohols and phenols have higher boiling points compared to alkanes and ethers. Essentially, hydrogen bonding increases the amount of energy needed to break these interactions, resulting in higher boiling points. Additionally, hydrogen bonding makes alcohols and phenols more soluble in water because they can form these bonds with water molecules. In contrast, ethers lack the ability to form hydrogen bonds with water, which leads to their comparatively lower boiling points. This difference is a key factor when we consider the physical properties of these compounds. Now, let's talk about acidity. The general trend is that phenols are more acidic than primary alcohols, which in turn are more acidic than secondary and tertiary alcohols. This trend is primarily due to the stability of the conjugate base formed after deprotonation. Resonance stabilization plays a big role for phenols, making their conjugate bases more stable. Inductive effects also influence acidity, especially in tertiary alcohols, which are less able to stabilize the negative charge. So, understanding these concepts, nomenclature, hydrogen bonding, and acidity, helps us grasp the fundamental properties of these compounds. These are key ideas that are crucial for success in CBSE chemistry, and they tie directly into our overall understanding of organic chemistry. Now, let's look at some common organic compounds and their practical uses. Glycerol, for example, is found in cosmetics, pharmaceuticals, and even as an antifreeze. It's primarily used as a solvent and also serves as a precursor to other chemicals. Moving on to methanol, historically, it was used as an anesthetic, but today it's more commonly employed as a solvent in various industrial processes. Then there's diethyl ether, which has been used as a solvent, a fuel, and even in the production of some alcoholic beverages. Lastly, ethanol is perhaps the most familiar. It's used in beverages, but also as a solvent and in many industrial applications. These examples really highlight how these organic compounds are not just theoretical concepts. They have widespread, practical roles in our daily lives and in various industries. They exemplify the importance of understanding organic chemistry beyond the classroom, showing its real-world relevance.